So called to the new INDUS series because this is called a review series, and here we primarily focus on a particular work, a particular area, a review of a particular area associated with solar astrophysics. Our first guest is Prasad Subramanian. He is a faculty at IISER Pune. So he got his PhD from George Mason University at US. After that, he joined NRL, then IUCA, then IIA. So he is primarily interested in CMEs, coronal mass ejections, especially their heating and drag mechanism. And he is also interested in black hole accretion. So now he will be going to speak about the small scale fluctuations inside the CMEs and how it can affect the CME driven space weather impacts. So, sir, the platform is yours. Yes.
Thank you very much. I guess you guys can see the screen, right? The full screen.
And just one fact: the questions will be at the end.
Right.
Yeah, sir, please.
You guys can see the screen, right? The full screen.
Yes, we can.
Yes.
Excellent. Thank you. So, so today I wasn't quite aware that this was supposed to be a review talk. Well, it's a review of some of my recent work, so you'll have to forgive me for that. I will try to keep it as comprehensive as possible. So this represents work by myself, Debesh, Deep Bhuge, and currently Apurva and Sumit, who are working on some of the stuff that I'll be presenting a little later. So let's get started. I will be talking about a relatively less studied topic, turbulence, fluctuations in all physical quantities in coronal mass ejections, with a specific focus on Earth-directed coronal mass ejections, because we want to see if and how turbulence might have a bearing on the strength of the geomagnetic storms that the Earth-directed coronal mass ejections can cause. Okay, so this is obvious stuff. I don't need to repeat this. Coronal mass ejections directed at the Earth often drive large geomagnetic storms. The term geomagnetic storms, of course, encompasses a whole lot of effects and very complicated stuff, ranging from outer space, as I say, about where our L1 satellites sit, all the way down to very low Earth orbiting satellites, to effects on the environments of very low Earth orbiting satellites, to things on the ground, such as power outages, to spectacular displays such as the aurora, all sorts of things. It's a huge, complicated field, but it's generally understood, it's kind of accepted, that CMEs are often one of the main causes. So, having said that, this is common knowledge. I won't belabor the point. Most of the time, the properties of the CME that are thought to affect the intensity of the geomagnetic storm, specifically the DST index, are thought to be the direction of the southward pointing magnetic field at the leading edge. Leading edge meaning the part of the coronal mass ejection that interacts with the Earth's magnetosphere first. Okay, and things like the speed and the mass of the CME, basically the momentum of the CME, how much the CME can compress the geomagnetic field, and how well it can lead to reconnection, what the direction of BC tells you. These are generally taken to be the primary determinants of geomagnetic storm strength. The possible effects of turbulence, this is what we will be talking about in the leading part. And the leading part, which interacts first, I should have said first here. It interacts first with the Earth's magnetosphere. It's not very well very widely acknowledged. There are some exceptions, some of the pioneering work by Borowski and Funston, which talks about turbulence enhanced viscous coupling. So we will tangentially address this, but not much. As we go along, it will become clearer. So this is the kind of picture we have in mind. There's a sun right there, and you've got a magnetic. Let me emphasize: this is really a cartoon. We think so. This would be the coronal mass ejection, the cloud, which is propagating towards the Earth, and there's the spacecraft sitting very close to the Earth. And this is my poor attempt at trying to depict a shock that's possibly driven by the coronal mass ejection, ahead of the coronal mass ejection. Okay, so you've got a spacecraft sitting, and things like whether or not the legs of the coronal mass ejection are always connected to the solar corona, not really known. We will simply confine our attention to this, just the local part. Okay, so you've got a spacecraft sitting here very close to the Earth, 1.6 million kilometers above the surface, which is pretty much at the Earth as far as the Sun-Earth distance is concerned. And so for all we will be concerned with data that are sampled in situ. The word in situ means, at the site. Okay, so the spacecraft is as good as a point, and this huge structure just moves past the spacecraft like so, and so the spacecraft simply sits there and measures quantities. I will be showing you runs of temperature, density, and so on and so forth. I want to emphasize that these are not the primary measured quantities. These are quantities derived from the measurements. These are moments. We'll come to that. But this is the kind of cartoon we should keep in mind. And so the leading part of the CME the leading part of this entire structure could be the shock, or could be this part, this entire part, which is this entire part between the shock and the CME per se, which is called the sheath. Okay, I can't write very well with this, so I should have written this part between the shock and the CME is called the sheath, and that is typically so. Let me move on and. So this would be so this sequence is going past. Okay, so the spacecraft it first encounters the background solar wind. You see, it first encounters whatever was before the shock, the background solar wind. Okay, it first encounters the background solar wind, then it encounters the sheath, which is the part between the purported shock and the coronal mass ejection. Then it encounters the body of the CME, and so that's how. So the time axis of a typical data run, for instance, magnetic field would move like so. So you have the background solar wind first, and then the sheath, and then the body of the CME. The CME starts and the CME ends, so to speak. But you see, let me see if I've got like that. Okay, so time on the x-axis. So this would be the background, for instance. And the part between these two dashed lines would be the sheath, and then the part between the green dashed line and the purple dashed line, that's the body of the CME. Trouble is, the boundaries are not. This is just a cartoon, and well, it is it is what we thought what we think the structure looks like. But the crucial thing to remember is that the boundaries of the starting of the sheath, the starting of the CME, the ending of the CME, so on and so forth, are not known a priori. Okay, these can be determined only after substantial post-processing on the data. For instance, taking this time series data and fitting it to a force-free magnetohydrostatic model. Minimum variance techniques. So there are lots of ways one can go about it. Again, all of these involve a lot of assumptions. So in other words, what I mean is that these boundaries, the red boundary here, the green boundary here, this and the purple boundary here, this is not known a priori. This is our guess at what the structure looks like. And this is done, I mean, you obtain these boundaries only after a lot of post-processing. Okay, so that is something that I want to want you to keep in mind. And the kind of questions that we will be asking here is as follows. Are there concrete derived observables that can distinguish one region from the other? In other words, you might say, well, yeah, sure, here's the region. The thing is, these boundaries are marked only after post-processing. Without knowing these boundaries a priori, just from the time series data, with some relatively quick computations, can we distinguish one region from the other? For instance, can we distinguish the background from the sheath from the CME interior, so on and so forth, before the in situ data is fitted to a model, which is substantial post-processing. Okay. So I will go on. So please keep this in mind. And can the results from such an exercise be used to inform classifiers, semi-automated classifiers, to tell us when the spacecraft is transitioned from the background solar wind to the sheath and to the interior of the CME? This is the kind of motivation, the loose motivation, that I have in this talk. Although I started out by saying geomagnetic storms and so on and so forth, I will point out the relevance of this a little later on. Okay, so we've talked about this before. So time runs from left to right. The top panel shows the proton temperature, the total magnetic field. In fact, all three components of the magnetic field are measured. Typically, in situ measurements here, I'm only showing you the total magnetic field, the total velocity of the plasma that's blowing past the aircraft, and the number density of protons. Okay, so this is the kind, subsequently when I say time series, this is the kind of data I'm talking about. And and so the part before the red line, this part is called the background. This part in between these two dashed lines, this is called the sheath. And this part from here to here, this is called the interior of the CME, often called the magnetic cloud. It's a slightly different definition, and I'm not going to go into the details of those definitions. The thing is, all such definitions, is this a bona fide magnetic cloud? Is this a good flux slope, so on and so forth? All of these questions are relevant after you've fitted it to this data to a flux slope model, and that's substantial. That takes months, for instance. Even after the data is received. Okay, so right. So this is the kind of data that the time series data that we should keep in mind. And these are some preliminary. We started thinking about this sort of stuff around 2023. Well before it got published in 2023. This is Debesh's work, and so he part of his thesis. He gathered a sample of about 152 Earth-directed CMEs that conform well to a flux slope configuration. And so this is this obviously involves post-processing to determine this property, so that we can have good confidence in these dashed lines, in the location of these dashed lines. That's the reason we chose these 152 CMEs. And what he did was was the simplest possible thing. He would take, so this spans several days, of course. So he would take, based on the typical cadence of the data, he would take a running window, say about from here to here, okay? And he would let this window slide all through the time series, and he would compute the statistics in there. What's the mean? What's the standard deviation? Yeah, that's about it. As simple as it gets. Turns out there are lots of very interesting things that can be squeezed out of such simple results, and among those were things like this. Inside the CMEs, he was concentrating mostly on the body of the CME, inside the CMEs. And inside the CMEs, standard deviation of the magnetic field to the running mean. And so this gives you an idea of how strong these fluctuations are in comparison, how deeply modulated the magnetic field is. He did this for all sorts of other quantities as well. I'm simply giving you a flavor by pointing out the magnetic field result. Okay, so delta B is a standard deviation about 1 hour running averages, and he found that it's just about a few percent. Okay, about between 4 to 5%. So that's about how much the fluctuations, the turbulent fluctuations in the magnetic field modulate the background. And using this and using a whole lot, I don't have time to explain how he got this result, but you see, this is a collisionless plasma in that the protons rarely, or electrons as well, to a lesser extent, but the protons definitely rarely collide with each other. Any scattering that happens to the protons, which is what informs transport coefficients such as resistivity, viscosity, and so on and so forth, that is because of these fluctuations. So having a good knowledge of these delta B's allows you to calculate things like anomalous resistivity as opposed to the standard collisional Spitzer resistivity. Okay, so he found that anomalous resistivity exceeds the Spitzer resistivity by those sorts of factors. Why are we worried about this? We want to see if this kind of anomalous resistivity is enough to explain the additional heating that is thought to take place in the interior of CMEs. Turns out that the first order answer is no. These sorts of enhancements are not enough. Certainly not to explain bright spots or bright knots that are often seen in imaging data, of course, much closer to the sun. Okay, so there's a whole lot that can be done. There's just a very brief snapshot of this interesting sorts of results that can be got with this kind of analysis. Let me move on to slightly more recent work. I need a little bit of time to explain this. So this work was based only on moving averages. Okay, you take a one hour average, for instance, a 1 hour average window here, and you compute the moving average within this box, and you compute the standard deviation about that moving average, and try to see what you get. The other obvious thing you can do is simply Fourier transform. You're interested in fluctuations, simply Fourier transform. So you Fourier transform, for instance, if I'm interested in the sheet, you just take the stretch within the sheet and you Fourier transform. Not the temperature. For instance, you Fourier transform the magnetic field, or you Fourier transform the velocity. As simple as it gets. Okay. So the Fourier transform would be denoted by this quantity, b hat. Okay. And here I'm illustrating just these quantities for the sheet. This is basically for instance, if you were to do a Parseval's theorem, if you simply write on the left hand side b of t quantity squared dt, and integrate it within this interval, that should be the same as this. Here you're doing it in frequency domain. On the other side, you were doing it in time domain. That's Parseval's theorem. Says that both the quantities are the same. Okay, this gives you an idea of the amount of power that's contained in the fluctuations. Okay, and we call this EB. The dimensions vary with the dimensions of the quantity that you are talking about. In this case, it's simply nanotesla square. The dimensions of this per se would be nanotesla per hertz, and since you're integrating over frequency, the quantities, this would simply be nanotesla square or Gauss squared, as depending upon what units you use. Nanotesla is a commonly used units in this field. So from this, what we do is we simply divide it by the sheet's duration to get what we call the power of the sheet. So this quantity would be nanotesla squared per day for the sheet. Similarly, we can get the same quantity for the background, which we define. There are various ways of defining the background. One of the simplest things to do is just to say a stretch of solar wind that's 1 hour, 1 day, sorry, 1 day before the start of the event. We just call it the background. Okay, so that would be that stretch that the spacecraft will encounter first. This would be the stretch that it encounters second, and that would be the stretch that it will encounter third, right? So just like this, we can compute similar quantities for the background and for the interior of the CME. We can compute all three quantities, not just for the magnetic field, but also for all these quantities, for the solar wind velocity, for the proton density, so on and so forth. Why are we doing this? We're doing this so that we get an idea of the power. I'm using the word power loosely. Like I said, the units differ depending upon the quantity we're talking about. The details are in the paper. But these sorts of, just like you have a PV sheet, you can have a PV sheet, which refers to the velocity, and a PN sheet, which refers to the proton density. All of these say something about how much power is contained in the fluctuations of that particular quantity. And just like you can compute the quantity, the relevant quantity for the sheet, you can have it for the background as well as for the interior of the CME, right? So let me show you some results, right? So here's one representative result. This is a statistical average or a snapshot of these quantities, of these sorts of quantities, I must say. Since I'm talking about magnetic field, I'm showing you the histogram for the magnetic field only. We have such histograms for other quantities as well. But there's a snapshot over all the 152 CMEs that Debesh studied and Deep used later on. Okay, so what's this telling you? You look at, for instance, concentrate only on the blue bars, which represent the mean. So the mean of the power in the magnetic fluctuations in the sheet clearly overpowers what's there in the background and is larger than that in the MO refers to magnetic obstacle. For the purposes of this talk, you can simply think of it as the interior of the CME. Clearly, the blue bar is in the sheet is way taller than that in the background, and also that in the interior of the CME. Same for the median, same for the most probable values. It's just that the contrast for the mean is largest. Okay, so using quantities like this is a summary statistics table. So I will spend a little bit of time on this. So the ratio of the mean in the sheet to the mean in the background for the magnetic field is about 76, which is to say the ratio of the blue bar in the sheet to that in the background is about 76. Okay, the same thing for the velocity is about 16, 15.4, so on and so forth. Okay, so if you were to try to figure out a quantity that very obviously distinguish between the sheet and the background without model fitting, simply with simple Fourier transforms, which can be done really fast. Okay, these are between the sheet and the background. These are probably your best bet. Okay, the results for the density are not so striking. I could go on and say how density turbulence is a bit of an oddball in any case, but that will take me farther afield, and I don't want to talk about that right now. Okay, and so if you were to simply look at the largest number, the largest contrast, they're always between the sheet and the background. Okay, if, for instance, if you look at this, the ratio of the mean in the sheet to the mean in the magnetic cloud, that's, I mean, for velocities, it's a factor of 9, nothing to sneeze at. Even for the magnetic field is about 4.3. But always, if you look at the large numbers, it's always between the sheet and the background. In other words, the background is really quiet and the sheet is really turbulent. We kind of knew this already, right? I mean, everybody knows this, generally speaking, but we believe this is the first quantification of these quantities in concrete terms. So for instance, I'll just read out this paragraph. For instance, if the mean fluctuation power in magnetic field in a 1 hour running average, okay, so you see all of these are computed for the entire sheet, okay, but since I'm dividing by the duration of the sheet, if you were computing a Fourier transform for a 1 hour stretch of data, these numbers will be representative. Okay, so you take a 1 hour stretch of data, compute the Fourier transform, and quick, tell me what's the has the fluctuation power in magnetic field increased by a factor of something like 70? Oh, well then we have transition from the background into the sheet. Okay. If you want to make it even more robust, if this ratio is 70 and the ratio for the solar wind velocity is about 15, then we have likely transition from the background into the sheet, and so on and so forth. Okay, so this is one a useful way of determining when the spacecraft has likely transitioned from the background into the sheet and from the sheet into the magnetic cloud. Okay, the second one is not as dramatic, but in as much as the sheets are the leading parts of the CME structure that interact with the Earth's magnetosphere and spark off the geomagnetic storm, these numbers are probably the most useful. Okay, so that's as far as summary statistics go. As far as using Fourier transforms for the entire duration of the sheet, or the entire duration of the 1 day background, or the entire duration of the CME interior, as far as that goes. Now, it's a well-known fact, however, that these results only give an aggregate picture of the turbulent power in each region. For instance, the sheet or the interior of the CME. Okay, it's a well-known fact that when you take a Fourier transform, you lose all time information, right? You can slice up. In fact, we are indeed slicing. We are taking only the stretch that's relevant for the sheet. But the finer you slice, the worse your frequency resolution becomes. Okay, so now without going into details of what wavelet transforms are and so on and so forth, I'll simply tell you that this. Okay, before saying that, turns out that these turbulent fluctuations, the appeals that we make to quantities like this is an aggregate. There's an aggregate picture of the turbulent power in these regions. But turns out that these turbulent fluctuations are not uniformly spread out. In fact, concentrated in clumps. And this points to. So this is work that Apurva and Sumit introduced me to this way of looking at things, to the wavelet way of looking at things. So this is work that we're currently carrying out. And in some sense, this is the bottom line of this work. Turns out that the turbulent fluctuations are not uniform. They're concentrated in clumps, and this is what's called intermittency in turbulence. There are various ways in which people look at intermittency. Most of the time, they look at the non-Gaussianity of the statistics. The less Gaussian it is, the more intermittent. People look at other measures such as kurtosis and so on and so forth. But we here will show you a more using wavelet transforms, as you will see, we can arrive at a slightly more intuitive picture of understanding this aspect. Okay, so wavelet transforms you can think of as a magic tool that offers you both frequency as well as time resolution. Okay, it gives you a movie. So this is time on the x-axis, and this is frequency on the y-axis, and the color code gives you the intensity of the fluctuations. So the color code, the color code tells you the z-axis, the intensity of the fluctuations at this frequency, that frequency, so on and so forth. So it gives you the frequency distribution as a function of time. It sounds like magic. If it sounds too good to be true, it is. Okay, there are issues. The frequency resolution worsens at the time resolution worsens at low frequencies, and so on and so forth. There are issues, but still, this is a very useful way of looking at things. So what you're seeing here is an example. What you're seeing in the lower panel here is an example of a wavelet transform of it's not quite the wavelet transform. It's a frequency pre-multiplied wavelet transform of the magnetic field fluctuations for one particular CME. Okay, so and these dashed lines are the same things that we saw before. Before the dashed line, you've got the quiescent background solar wind. In between these two dashed lines, you've got the sheet. And in between these two dashed lines, between the green and the blue dashed lines, you've got the interior of the CME. Okay. So now, what can you tell from this picture? So clearly, for instance, inside the sheet, if the sheet was supposed to be uniformly more turbulent than the background, you would see a sort of a, this would be uniformly, more or less uniformly filled with yellow. Maybe not very bright yellow, but nonetheless some more yellow. You see, yellow is more intense. Okay, clearly it's not. Okay, so you see streaks here, spanning over a wide range of frequencies. Okay, you see streaks. So yes, you can simply look at it and say that there are more streaks here as compared to here. There are a few streaks here also, but definitely this is the more streaky portion. Yes, but the thing is, it's not uniform. That's the whole point. The turbulence, the fluctuations over a fairly wide range of frequencies seem to be concentrated in clumps in time. Okay, at this time it's larger, at this time it's larger, so on and so forth. And this points to the poor time resolution at low frequencies. Okay, so not to just to and the top panel, what that is again, it's time on the x-axis. And you integrate, instead, I choose to sacrifice the entire frequency resolution. I just integrate over the entire frequency axis. Okay. And I plot a light curve-like thing just to improve my time resolution. Okay. This is something Sumit helped me understand over. It took me time to understand, but we finally did. So, the thing is, you see this streak, okay? It shows up as a nice little peak on this curve, okay? So all we need to do, if we want to localize the time position of these streaks, all we need to do is count the peaks, okay? For instance, if I was interested in knowing how many turbulent spots there were inside the sheet, I simply count the peaks, 1, 2, 3, so on and so forth. Okay, so this is the quantity that's plotted here, integral of the spectral power. Okay, and so this is an example of what I call a turbulence spot. There are so many other examples. So what we do is, let me see what I've got in the next slide. Yeah, right. So what we do is we take a given event, okay, and we simply, there are so many spikes here. Okay. So we want to say arbitrarily, I take the top 10 spikes, okay? Only the most intense of the spots. And I ask, of those top 10 spikes, how many are in the background, how many are in the sheet, and how many are in the interior of the CME? Okay? And the results for all the 152 CMEs that we have studied are as follows. I'm really sorry this got cut off. Okay. So the red represents the sheet, the blue represents the background, the yellow represents the magnetic cloud. Never mind the temperature here, we will talk about that later, but this is for This is for just this, what we talked about. There's one example of for one quantity for one CME. Okay, so this would be the spectral power, the wavelet spectral power for magnetic field fluctuations, velocity fluctuations here, and density fluctuations last. Okay, so what this is saying is that on an average, this is what's plotted: the number of turbulence spots per day. On an average, you've got 20 turbulence spots per day in the sheet, about 1.6 turbulence spots per day in the solar wind background, and about 4 turbulence spots per day in the magnetic cloud. So in some ways, this is kind of painting the same sort of picture of a very turbulent sheet, and as compared to the background, definitely, and a moderately turbulent CME interior, except we are not talking about turbulence. We're not simply talking about the turbulent power. We are talking about the number of turbulent spots, the number of such spots. Okay, so you've got 20 odd spots per day as far as magnetic field fluctuations are concerned, about 9 spots per day as far as velocity fluctuations are concerned. Also about 9 spots per day as far as density fluctuations are concerned. Okay, and in all cases, the brick red part, which represents the sheet, far overshadows the blue bar. Okay, and this is our main result. Okay, so moving on. So this is what I mean by saying that the turbulence is clumpy or intermittent. It's not uniformly spread. It's organized into spots. So CME sheets are characterized by significantly more turbulent spots. Oh gosh, all of this got cut off somehow. So about 20 odd magnetic spots per day. Okay, about 9 odd velocity spots per day, and about 9 odd density spots per day, as compared to the background and the CME interior. What's more, and this is the really interesting part, sheets are also characterized by more enhancements of the proton temperature. And here we're not talking about any sorts of wavelet transforms or anything. Look at the proton temperature. This is just the proton temperature, no fancy transforms. There are more spikes in the proton temperature in the sheet. It looks like it, okay, but we've counted it, all right, in the sheet as compared to the background. And what's more, we have about 21 per day. That's what this is saying. About 21 spikes at 20 on the average. You've got 21 peaks in the proton temperature per day, as opposed to 0.2 per day in the background. This refers just to proton temperature. So that is one thing. But this is a really interesting result. Each proton temperature peak has about 2 neighboring magnetic field turbulence spots. By neighboring, I mean within 70 minutes. Okay, 1.8 neighboring velocity turbulence spots and 1 neighboring density turbulence spot. In other words, these turbulence spots, if you see a turbulence spot in the magnetic field, it's most likely going to have a peak in the proton temperature within about 70 minutes. Okay, so clearly this is pointing to the turbulence spots being sites of localized heating, and this gets, I mean, this is something that the plasma physics community has been wondering and thinking about for a long time. All sorts of fancy plasma physics goes into it, transitioning from the fluid picture to the kinetic picture, exactly how protons are heated, what sort of mode conversions are happening, and so on and so forth. You can speculate and theorize all you want. This is evidence, okay, that the turbulence spots. So if someone asks you, what are these turbulence spots you're talking about? One way of answering this is point to the wavelet spectrum and everything. The other way of answering it is, well, these turbulence spots are sites of localized heating. Localized heating of who? well, protons, most likely electrons also, but electron data is much messier, so we chose to look at the protons first. Okay, so so physics-wise, this is the most interesting result. Practical space weather forecasting-wise, these are the most interesting results. That sheets are characterized by more turbulent spots. That's it. It's yet another way of so the number of turbulent spots per unit time, in addition to the overall turbulent power that we talked about earlier. There's a useful discriminator between the solar wind background sheet and magnetic cloud. Okay, so and why is this important? Most of the time, the sheet, well, almost always, the sheet hits the geomagnetic field first, and therefore that's what causes the storm. So it would be nice to have a much faster way than you know, post processing and everything. You know, of course, you know when the CME left the Earth, left the Sun. I beg your pardon, and when it's likely to come. Of course, the distance estimate, the time estimate depends upon details of the CME propagation and so on and so forth. But a much finer. I mean, so those sorts of alerts are of the order of, you know, several tens of hours, maybe of the order of a day or something. But this would be a much finer alert, an alert to within a few hours. You know the storm's going to hit, but hey, so we transition into the sheet, and therefore the onset of the storm is imminent based on these parameters. Of course, this is using data from L1 spacecraft, and in any case, the CMEs, the overall transit time of the CME from L1 to the magnetosphere is about an hour or so, maybe 2 at most. So as such, these results are only indicative, but they can be especially useful if we could have routine sampling of in situ data at points that are closer to the sun than L1. Okay, for instance, I mean, these sorts of things can be done using solar orbiter data, but of course the solar orbiter is not stationary; it keeps orbiting, and so it's not all. So this could be a case made for finer level space weather alerts using in situ data from spacecraft that are situated a little closer to the sun than L1. So that's about all I have to say. Thank you very much. I'll take questions.
Thank you, sir, for your work and review of the whole thing. Yeah, the platform is now open for questions. I think Shatabdo has a question. He has raised his hand. So yeah, please speak.
Okay, first of all, thank you very much for this very nice and interesting presentation. I have 3 questions. I don't know if I'll be allowed to ask all 3 of them, but I'll just pick the first from the top of the stack right now. The first thing is about can you go back to the plot where you showed the distinction between the background, the magnetic cloud, and the sheath, where you have these 3 histograms stacked against each other?
Yeah, sure.
Yeah,
which one?
Just the next one.
This one?
Yeah, this one, yes, correct.
Yeah,
so for the density, I found that the background and the magnetic cloud seems to be very similar to each other. Why is that?
Yeah, don't know. No idea.
Okay.
No idea. Right. These are we haven't thought so much. No idea. Simple answer.
Right.
I'll tell you the other thing, the other grumble I have about density fluctuations is that it never fits neatly into any kind of turbulence theory. Okay, density is, I mean, you know, you look at turbulence theory in general, MHD turbulence theory, they only talk about velocity and magnetic field fluctuations. Then it's always thought to be incompressible turbulence. At least that's where the theory is cleanest. Compressible turbulence, which involves density fluctuations, is a bear. Okay, And so yeah, I'll just that's neither here nor there, but I wanted to say it anyway. Yeah.
Mm-hmm.
Yeah.
Dinesh, can I ask another question?
Sure. Thanks.
Okay, thank you. The next one is, so it seems like your whole work sort of revolves around this idea that you have this 1 hour moving window of averaging. And my question is, on what grounds do you consider this 1 hour window, or
data cadence? That's our typical data cadence. That's
okay.
All. Yeah, just typical, so that you have enough points to make a meaningful moving average. A meaningful moving average, or to compute a Fourier transform or a wavelet transform, as it might be. Yeah. So for instance, here the meaningful, this is a wavelet transform, and a meaningful distinction can be made between one thing and the other over time scales of about an hour. Yeah, just based on the cadence of the data. Yeah.
Right. So then that sort of brings me to the third question, which is my last question. That, well, for missions like Parker Solar Probe and Solar Orbiter, we obviously have really much high resolution data.
Sure. Oh yeah.
So based on that, how would you expect the turbulence to be more? And on that same question, you ended your talk with this idea that you can use this as a sort of inference for sub-L1 monitors. So my question would be that this sort of amount of turbulence, or the number of turbulence spots that you get to see inside a part of the CME, be it the sheet or be it the magnetic cloud, would you get any correlation between the number of spots you see and the size of the sheet, for example, let's say?
We are dividing by the sheet duration. You see, this is always per day. It's always per day. That's how we're removing the size of the sheet from the equation. It does not matter. It's always per day or per hour. So my guess is these ratios won't change much.
Okay.
Yeah, that's my guess. We'll have to see. Yeah, you might see much more. You might see finer detail, but the ratio. If you're sampling, you're taking a 1 hour sample, and you're quickly doing a fast Fourier transform, or maybe not a full wavelet transform, just a discrete wavelet transform for speed, and then the number of spots, for instance, the total turbulent power jumps by a factor of x, and that x, I think, this is quite indicative. 20 divided by 20.03 divided by 1.58, whatever that is, for instance, or this table. This ratio won't be terribly different. That's my guess. Yeah. But the number of spots, physics-wise, you could probably unravel a whole lot more, much more interesting things with higher cadence data. Definitely. Oh, yeah.
Okay. Thank you.
Yeah, I think there is a question in the chat. So, Angelos, if you want to speak out, so you can speak and ask the question to speak.
Okay. First of all, thank you for the talk. It's a really interesting topic. My question is actually two questions. It's if you checked if there are differences between fast and slow background solar wind, and the second is whether you checked if the speed of the CME plays a role.
Neither. We haven't checked. We've simply taken as large a sample as possible to get. We haven't sliced the data like that. I'm sure there are trends. I'm sure there will be trends. We simply haven't done it yet. Yes.
Yeah, that's my intuition as well, that there would be differences.
Definitely.
That's why I wanted to ask.
Definitely. We were simply, it was the first time we're doing it, and we simply wanted to see, just from a purely operational point of view. No matter what the CME speed, 150, it covers all sorts of CMEs. Okay. And so this is summary. These are averages over a large sample, and so that was but I'm sure there will be trends and clearly interesting things to look into, obviously. Yeah. Thanks for the suggestion. Yeah.
Indeed. Thank you very much again.
Thank you. No more questions, huh?
Yeah, I think, yeah, please speak.
Oh,
Hi.
Mishka, hi.
Hi, sir. How are you?
I'm doing well. I'm doing well. Yeah,
Yeah,
yeah.
this is great. Thank you so much. It's
That's awesome.
nice to see like a statistical study of this.
Right.
I'm just going to piggyback on what Angela said. I think you will also see something like a variation over the solar cycle also. And if you or if your students do look at the types of CMEs in terms of interacting or isolated, that will also probably give you some extra information.
Sure, sure. See, all of this, I would say, falls into the physics basket. And interesting, of course, needless to say, all sorts of delicious detail. And I mean, I'm not even, for instance, things like why is it that these spots are sites of proton heating, and all sorts of, and does this are faster or slower CMEs quote unquote hotter in terms of proton temperature spikes and so on and so forth. We haven't even started scratching the surface. All kinds of interesting things. We just wanted to get an aggregate picture. Yeah.
Can I ask another question, Devesh?
Sure.
Okay, so with the simulations and models, we don't necessarily capture these really turbulent structures in corresponding like in situ measurements, like from the simulations. But what we do have in models are, for example, alpha wave turbulence. Is there something that we can or something that we can find like a correlation between these?
Sure. See, you have to ask, what is the nature of this turbulence, right? And there is the guess is people have looked at people like the Mumbai University folks, Anil Raghav, and those are the that's the work that immediately comes to mind. They published several papers, and I'm sure other people also. They looked at a lot of such people look at the alphanicity of the So, and most of the time the conclusion is yes, quite alphanic and so on and so forth. But once it comes to, I mean, all of this is holds only for the fluid part, and does not, it does not capture the intricacies of when you transition into the kinetic regime. Sure. The trouble is, look at these density fluctuations. Alphane waves, incompressible. Density fluctuations are there. The data is just showing you density fluctuations. So the nature of the turbulent fluctuations, big question. And testing the alphanicity or lack thereof of these fluctuations, relatively straightforward thing, not too difficult. It's doable. I mean, it involves some efforts, and that's something that can definitely be correlated against, and that can be definitely be checked, correlated simulations. Yes. Yeah.
Okay. Thank you.
Arpit?
Yeah. Hi, very nice talk. It was very interesting. I'm first time seeing this kind of talk, and the physics wise, it is very interesting. So my question is, why these turbulent structures are intermittent, and is there any periodicities associated with turbulent structures or not? This also boils down to the question, where is this turbulence is coming from?
You ask difficult question. I'll say I don't know all three questions. We don't know. Okay. Where is it coming from? Oh boy, solar wind. Even the quiescent solar wind is turbulent. You see, and this is just observed fact. And people try to figure out the nature of the turbulence. Okay, where it's coming from? Most likely jigglings at the foot points. The fact that the fact that how should I say? the motions of the foot points of the magnetic field anchored in the solar corona, they are not uniform. They jiggle, and so waves are excited and they travel along the large-scale magnetic fields, and nonlinear interactions sort of create smaller and smaller turbulent structures, and resulting in what we see as a fairly saturated turbulent cascade, conforming. And now I'm going farther afield, conforming sometimes to the Kolmogorov spectrum that's expected for fluid turbulence, but MHD turbulence has no right to be doing that. So where it originates from, the most common sense guess is probably jiggling of the foot points. That's the mother of it all. And you ask a few other questions. Are there periodicities in why is the turbulence intermittent, you ask? That too, I don't know. Okay, this is probably just a reflection of the fact that the turbulent cascade is highly nonlinear. Okay, nonlinearities often give rise to such isolated structures. Okay, soliton-like structures. I'm not suggesting that these turbulent spots are solitary structures. That's not what I'm suggesting. I'm simply saying that nonlinear interactions often give rise to such phenomena as isolated structures. Okay. Periodicities and intermittence, I don't know. I've certainly not checked.
Okay. Thank you so much.
Sure, yeah. Okay, so I guess.
Yeah, I just want to add a small thing to what Shatabdu asked, that whether the fluctuations are a function of the size of the sheet. So from our recent work, which was accepted in JAA, we have seen that no, they are not actually. So size of the sheet is not important, right, for the fluctuations. Like the amplitude of the fluctuations is almost independent of the size of the sheet.
I forgot to include that stuff. Yes, sorry about that. Yeah, there's more work. Yes.
Yeah. So I think that's also true for the size of the cloud, because what we found from our J work that these fluctuations are really kind of fundamental into the plasmas, and it's not a size, like it's not associated with the macro scale thing. So it's a very small scale structure.
But it's also indisputable that the sheet, while it's generally recognized as a more turbulent region,
That is true.
we've quantified it, so that's more turbulent. That's So
that's true. Absolutely true.
Yeah, that's kind of comforting. The actual well, in this talk, we've divided by the sheet duration. So we've taken the duration of the sheet, or the size of the sheet, out of the equation. It's always per hour or per day, as the case might be. That lends itself to a more operational. It doesn't matter. You're just sampling. You're closing your eyes. Things are flowing past you, and in any given interval, once the statistic jumps a certain ratio, most likely you transition. Yeah. So from an operational point of view, that is a slightly more useful thing. Yeah. All right. You can probably hear the Ganpati music blaring from outside. Yeah, it's all very lively. Yeah.
Yes. Yeah. That's true.
Right.
Pune thing.
Right. Yeah. All of Maharashtra. Yeah. No.
Yeah.
Yeah.
That's true.
Just one more point. I'm just thinking out loud probably at the moment. So we have already transitioned from this old view that about the self-similar expansion and stuff about CMEs that we have. And now would you say that based on the analysis that have been coming up in the last few years, based on measurements of turbulence inside ICMEs, would you say that, well, CMEs are not really coherent structures?
No, I won't say that. In fact, that was one of Devesh's first papers. They are. In that the large scale structures are the how should I say, the alphane talking time between the what was the result, the time it takes for alphane communication between the entire between the front and the back of the magnetic cloud.
Subalphinic, actually.
Subalphinic, exactly. Yeah. So
the information is slower compared to the speed of the alphine wave from one point to the other.
So they are coherent structures in that sense. The large scale structure is definitely coherent, but there are these bubblings happening inside, just like it does in the solar wind also. Solar wind is also turbulent. The background quiescent solar wind has been known to be turbulent forever. And there's a huge community of people who work on this, various aspects of it. So, yeah.
Right. Thank you.
Yeah, sure.
So, any hands or any questions in the chat? So, not, then thank you for your review and summary of all of the work related to the small scale fluctuations in the ICMEs and their effect. Thanks a lot. And also,
my pleasure.
Yeah, it's also our pleasure to invite you and to hear from you regarding our work.
Yeah.
And also,
Nice.
and also from all of us, it's also a good community here in INDUS. So you are it's your first time in INDUS, so that's the thing. So
Right.
INDUS
Thank
also
you.
welcomes.
Nice seeing so many familiar faces and familiar names.
Yeah.
Yeah.
Yes.
Thank you all. Yeah. Thank you. Bye-bye.
Thank you. Yeah.
Yeah.
Bye.
Bye.
Yeah.